Okay everyone, so we have been talking about the properties of vector spaces for some time now. When we formulated the axioms of a vector space, we had three rules: a rule of addition, a rule of scalar multiplication. Let's recap a little. The axioms were the rule of addition, scalar multiplication, and closure. All right. So we have actually been giving a simplified view of vector spaces to you. We said that there are three rules, but well, actually, in rigorously mathematical formulations, you will see in books that there are actually 10 rules. So some we said addition as one rule, but actually this addition operation has to satisfy some sub rules, you can say that. Okay, similarly the scalar multiplication has to satisfy some sub rules, and this closure property has to satisfy some sub rules. So if we take into account all those rules, then we will actually need 10 rules. But for our purposes, if we keep in mind these three rules generally, we will be able to work with our things. All right. So the second rule, on the basis of the second rule, that what type of numbers, on the basis of the type of numbers that we will use to multiply our vectors, we can um, classify vector spaces into two major types. All right, if these numbers are real numbers, then we call the vector space, well, on the basis of the scalars. If the scalars are real numbers, then we call that vector space the real vector space. Real vector space. If the scalars are complex numbers, then, well, simple enough, we call the vector space a complex vector space. All right, complex vector space. Okay, so as you know that all real numbers are a subset of the complex numbers, so the complex numbers are a more general type of the complex vector space is a more general type of vector space compared to the real vector space, and in our course we will mostly be working with the complex vector space. Okay, so actually uh, we can show that any all right, uh, all right, we will now view see another important property of vector spaces, the concept of inner products. Okay, the concept of inner products. All right, so what are inner products? Actually, it can be, well, quite easily shown that any finite dimensional vector spaces, vector space is equivalent to the space of, well, the space of n by 1 matrices, n by 1 column matrices. Actually all finite dimensional yes any finite dimensional vector space is actually equivalent to the space of n by 1 column matrices, where n represents the dimension of the vector space. Okay, so whatever operation we can do with a finite dimensional vector space, we can actually do that with this space, the space of all n by 1 column matrices, and that will be entirely equivalent. All right. Okay, so from now on we will be working explicitly with this set. All right, and for the purposes of quantum computing we will mainly work with the space of finite dimensional vector spaces, but general quantum mechanics is actually works with infinite dimensional vector spaces. For quantum computing we don't need to worry about all those infinities, and we can be content with finite dimensional vector spaces. Okay, since all finite dimensional vector spaces are equivalent to this set, we will be explicitly working with n by 1 column matrices or column vectors as our vectors.